Hello, Amiga coders. This is Photon. I hope you can hear me without distortion this time. Let's continue with our demo here. The title of this tutorial has to do with program structure and the stack, which I have mentioned fleetingly, and interrupts. At the moment we can have a look through the source, and it starts with a big block of commentary and constants for the music player. And I wanted to talk about interrupts because even if you don't call the main loop, you'd still have something on the screen, and you'd still hear the music. Well, it just exited, of course. How stupid of me, but if, let's say, we were to comment this out, this is a quick way to do that, with a conditional statement in ASM1. Even if we do nothing, the music will still play, and that's because it's playing on the interrupt. As you can see, there is some uninitialized screen data there, because the scroll routine has not been called. The copper is in its unmodified state, but the music still plays. So that's because it runs on interrupts. And interrupts are just what they sound like. They interrupt the execution of the main line code to do something temporarily and then return to continue off where it was. There's no telling when or where in the code the interrupt will seize control. All interrupts will just say, thank you, that CPU is mine, now I will do something for a little while, and then I'll return to you when I'm done. So first off, the structure. So if we go to the main loop and remove this conditional statement, I thought I'd start by making a neater structure here, because if you have multiple parts in your demo, then you like some way of calling a chunk of code that does a set of things, a number of things, without the check for a mouse press and so on. It's a way to make it modular. So let's go to the frame loop start, because we are going to completely remove the frame loop. Not quite, but I'll show you later. So Control X on this, and we want to put that in a subroutine. So we'll just insert a subroutine here, and a subroutine is something that's called on the stack. We want to replace the main loop code, because we don't. The only reason to restructure your code, is because you want it to be more readable, more navigable. You want the important stuff near the top, and so on. To call a subroutine, you can use JSR or BSR. These are not bizarre instructions. They just branch to a subroutine. That's the abbreviation for it. And let's call this part 1. Let's say. And all you need to do is create a label called part 1 and make sure that you return from subroutine when you're done. I've explained this before, and now we can remove the comments about frame loops, because no matter what frame loop we're in or wherever we are, we can call this chunk of code whenever we want. It's just like a function. This in turn calls various subroutines. So Also, we would like to perhaps add these magical statements that save all registers to the stack and restore them before returning. So that's a good practice. If you are running out of CPU time, I will show you that there's no danger of that at the moment. Then you may consider optimizing these, i.e. checking which registers you actually change in the subroutine and only save and restore those. But for now, it's good practice, so let's do that. You can also make a macro for this because you may have it in various places. I use push A and pop A from my Z80 days. So that's our subroutine. Let's put a name, for example, effect 1 subroutine, and we have replaced the big chunk of code that made it hard to read the main loop code by a single call, function call to part 1 there. So let's save this and check that there's no difference. As you can see, it executes normally, and this brings me to another point, which is that when a music player or any other high priority interrupt is playing in the background, it will, as I said, interrupt execution of what you're doing at any time and do its thing and then return to the mainline code. And this can sometimes mean that you get a stutter. In this case you don't, because the tempo is fortunate. The song is made so. But if you've tried to replace the module with one of your own and it uses CIA tempo, then there will be a high level 6 interrupt that may interfere with this raster weight. So what we will do is we will remove the raster weight. Mainline code loops, like these main loops, are good for trying out things, but when you make your demo proper and add music, you really should put your effect code in the vertical blank interrupt. And in tutorial 36, I added the friendly wrapper around our code that makes all of the whole demo system friendly, with an init and an exit of its own, and in doing so I removed some parts of it. One part of that was the vertical blank interrupt template. I've actually prepared this so that now that I have this branch to subroutine in my clipboard, I can go to the vertical blank interrupt, and where it says do stuff here, you can just insert it like that. Let's go through this. The vertical blank interrupt is sort of like a subroutine. The only difference really is that at the end of it you have an RTE, which stands for return from exception. Because an interrupt is a CPU event called an exception. Now, fortunately, we save and restore all registers in our effect code, so that this statement, which seems, well, there's the wrong dash there, it should be a dash, not a slash. This seems incorrect. If you want, you can change it for safety, but in this case, outside the subroutine, we are only writing to registers A6 and D0 down here. This means it's still correct, but it's good practice to if you add something later here and you had forgotten this, then you'd have a bug on your hands, and you'd have to find out why the bug occurs. So in order to save such dreadful moments, we make it safer like that. Let's go through the vertical blank interrupt. Here is just an initialization to make A6 point to the same custom chip base address that we use in the main loop, so that we can in fact move effect code from the mainline code into this interrupt. Because when the interrupt strikes and this vertical blank interrupt is called, there's no telling what'll be in the registers. You may have temporarily changed the A6 register to point at something else, and then you would then you could not rely on its value simply. So you have to set it, and then we test a bit in the interrupt request read register, which is many custom chip registers have write versions and read versions. Previously we cleared the interrupt requests in the write register, but the custom chips present the current state of the interrupt request bits at another address, simply in another register. So we read this bit, and this bit 5 corresponds to this value down here, and that's the bit that tells us if this interrupt is a vertical blank interrupt. And if it's not, if it's another type of interrupt sharing the same so-called vector, then we skip the entire code because it's not ours. We just skip it and restore the registers and exit. If it is ours, however, then it's a for real vertical blank interrupt. This will be executed at the very top of the frame. Previously we had a raster wait for raster line hex 2a, which is just before this vertical start position of the screen. But now when this vertical blank interrupt is called, it will be called about a centimeter above my mouse pointer there, a centimeter or two above it, and that may affect any timing code that we have in this effect code. I think it will not. And if you write code normally, it will not. What this means basically is that this piece of code, just like the main loop before, will be called 50 times per second at the start of the frame, just as our main loop waited for this position 50 times per second and then executed this effect part. When we're done, we have to clear the request bit. We do this by loading a value into a data register and writing it to hex D09C. This, as I've touched on before, is a 16-bit offset to the base address register A6, so that DFF000 plus hex 9C becomes this address. It's very useful. And that's interrupt request, the write only version of the register. So that's our vertical blank interrupt, and this ensures that this ensures mainly that our wait loop for raster position hex 2a, this wait that we had at the start, the CPU busy wait that we had at the start, will not be skipped due to an interrupt coming in from the music. So a lot of talk for a replacement, which is basically the same thing as a replacement for a frame loop. And when we go to the main loop, then all that we need to do really is, instead of busy waiting with the CPU, running our effects until we press the left mouse button, the code is now executed automatically by the interrupt 50 times per second, and all we have to do is wait for the left mouse button to exit the demo. So really, this label can be renamed to wait mouse, because it's a sort of a loop, I guess, but it's certainly not a main loop. So you may wonder, so when it comes to main, it doesn't do anything. Isn't that wasteful? No, it isn't really, because now you have freed the CPU to do anything you want asynchronously. That's a difficult word. So while you wait for the mouse, the interrupt will be executed faithfully 50 times per second, and you can do anything you want here. Things that take more than 1/50th of a second, you can do renderings, you can load files, you can do anything you want here. Either way, this is the correct way to do it. And I will only talk a little bit about other addressing modes. So here in the vertical blank interrupt, I can talk a little bit more about the stack. This is also an addressing mode, and this strange register here called SP is the stack pointer. That's a pointer to an address in memory that will decrement for everything you add to it and increase for everything you read from it. This means that the stack behaves like an upside down pile or heap, so that you can nest calls like this. It will push some stuff on the register, it will push the address of this subroutine onto the stack together with some other data, execute the code, and when it reaches the RTS instruction, it will pop those items from the stack and return to where it was. It will push the current program counter position, the address where this instruction is in memory, onto the stack, call the subroutine, and restore the program counter to continue off from where it left. So the stack is an inverted pile or heap, and this makes it possible to nest calls and to save and restore things without having to declare variables for all of them. Those of you familiar with other languages and also other assemblers will of course know what the stack is and how it behaves. This addressing mode then is called a pre-decrement addressing mode, and what it does is it tells the CPU to push each of these registers, and for each register it will decrement the stack pointer, and the stack pointer is address register 7 at all times. So SP is just an acronym or replacement symbol for address register 7, and that is the reason why we don't push address register 7 onto the stack. So much about stacks and addressing modes, and it's time to test if this works. Let's save it first. I've decided to release ASM2. This is my own little joint. This is my own little version of ASM1, which is the latest original version from Rune Gram Madsen, the Danish coder in Kefrens, once upon a time. And I've built upon that and made assembly and execution compatible with all CPUs and caches and so on, and added a few other things. Let's test our. I will go through the added features in the next tutorial, but feel free to download ASM2 and see if you can find some of the added features. For example, you can select text and you can Control X, Control V, and there's a PC mode that lets you use Shift to mark things. If you have misaligned comments, you can press Amiga tab and get a nice straight column, and some other things. I will show you one thing from ASM2 before I finish. But first, let's. I can show you another one. To assemble and to save a backup of the source and assemble it and run it, you can press Help. So as you can see there, it looked exactly like when we didn't call the subroutine. So the conclusion must be that this is not called. The vertical blank interrupt is not being called. And that is because we have not enabled the vertical blank interrupt. So if we go to our label demo, you can see here that we have some initializations to do. Here we initialize some values, and here we set up the copper, and here we initialize the music before calling the main loop. This is a neat little structure for a demo. It's short and concise and can be read easily. Since the wrapper takes care of the saving and restoring of copper and interrupt bits and interrupt vectors and so on for us, all we need to do is point this vector, which upon entry to the label demo has a base address in address register 4. This is for compatibility for accelerated CPUs that have a vector base register. So the vector base register is an A4 on entry. This means that we can put our address for the vertical blank interrupt into the vector offset for the vertical blank interrupt, which is hex 6C, as a 16-bit displacement from the vector base register. You will do this a lot and not think twice about it. I may explain how the vector base register works on accelerated Amigas in a later tutorial, but for now, this and this, sorry, is all we have to do. So set vertb interrupt vector compatibly, and enable interrupts generally and vertb specifically. So here the highest bit is set in order to set bits into this register, as I've explained previously in some of the first tutorials. The second highest bit is to enable interrupts generally as a sort of a master switch for all the interrupts. And then if you can maybe recognize this value that we cleared in the vertical blank interrupt, this bit enables the vertical blank interrupt so that it runs. So this means that it should now run as it did before. So we're back to square one, but we've now ensured that the raster wait that we had in our main loop before, first of all, we've ensured that we don't busy wait with the CPU, which is a good thing because you can do other things with the CPU then. And secondly, we've made sure that the raster wait isn't interrupted, so that if you replace the module, you could get a frame stutter. Finally, I will show you a feature of ASM2, and that is code folding in the simplest possible way, because I wanted to keep ASM2 usable on just an Amiga 500 with 512K extra slow extra memory, which meant that, well, that's the reason I chose chose to make the old small memory footprint version of ASM1 compatible, rather than just picking up the already pretty compatible ASM Pro source code and add my features to that. This is what I support, and I wanted to make something that I could use on my own Amiga 500. So there are two ways to fold code. Either you can mark it like this and write it as an include, or in this case you can just type an include statement, specify a name, p61 options.s, let's say, for the source file. Then you proceeded with a semicolon curly brace, and we want to fold all this very well documented p61 options that we chose for our tune here, and end it with a closing brace like that, with a semicolon before it. This allows you to simply double-click the include, and it has created this file then on the disk. It says writing file done, and if you should happen to want to look at these options again and perhaps change them, you can just double-click it again to open it, change it, and then fold it back up. So that's one of the features of ASM2, and I hope you have a good and happy new year and a really good 2016. Thanks for watching. Bye bye.